Today we are going to see how we can have a equivalent spring systems. Okay, so here you can see this one frame is there, and we are applying load P, and we can have a equivalent cantilever beam, okay, or you can have a equivalent single degree of freedom systems. Okay, so if you have any complex structures, and if you observe that you can model it using a single degree of freedom systems, in that case in such case you can have a equivalent stiffness and you can model it. Okay, so for example, for this case, if we have a frame, okay, and if you have fixed support conditions, okay, like this, then our displacement, lateral displacements, if you apply load P in this direction, then your lateral displacement delta, that will be your have a displacement like this. Okay, so here alpha is the ratio of your second moment of inertia of the beam and the column, okay, and this is the ratio of length of the your LB by LC. So here what I have done for this case, I assume all are the same. IB is equal to IC and LB is equal to LC. Okay, so in that case, what happened? You will observe the delta, that is equal to 6 plus 4, 10, and here 7. So 10 by 7 into PLQ by 24 EEI. Okay, PL. So 10 by 7 multiply PLQ by 24 EEI. Okay. So this will be your lateral displacement, and you will have equivalent stiffness like this. Okay. So what we can do, we can model this complex frame structure into the equivalent mass spring systems. Okay. So now if we want to do air static analysis, in that mass will not be a factor for you. You can assume any mass and you can apply unit force, or you can apply the same P force, and you can see whether you are getting the same reflection or not. Okay, so what I will do for this case, I will consider one example problem where the property of the material will consider as a steel. Okay, will consider as a steel, and your Young modulus, that will be your 20. Young modulus will be 200 GPa, and here we will apply unit force. Okay, and we'll try to see how much displacement, how much we'll apply unit force. Okay, and we'll see how much displacement is coming. Okay, so if we know how much displacement is coming, and if you know how much P is acting there, then we can calculate the stiffness like this, P by delta, that will be your stiffness. So we know that force is equal to K into delta. Okay, K into delta. So stiffness, then the stiffness will be P by delta. So if we know how much delta is coming, we can calculate equivalent stiffness for the systems. Other way is that you apply unit displacement and see how much force is required. So force is required for unit displacement, also that is your stiffness. But here what we are going to do, we are going to apply some force, and we are going to see how much displacement is coming, and then force by displacement, that will be your equivalent stiffness. So what we are going to do, first we are going to see if we have a cantilever problem like this. If you have a cantilever problem like this, and if we apply a P force, how much displacement is coming? As per theory, how much displacement is coming? As per theory, it should be PLQ by 3I. Now, if we have a frame system, then how much displacement is coming? As per the theory, it should be your this one. So 10 by 7 PLQ by 24 EI. Okay, and if we consider a mass spring systems, and if we apply that equivalent stiffness, then how much displacement is coming? That we are going to see. We are going to model it in Abacus. And one more thing we'll do, that we'll to make it rigid. If you want to make it rigid, in that case your EI should be high. So EI should be high. So here I am not going to change that geometry. What I am going to do, I am going to change the E value such that EI terms will be high, and it will behave as rigid, because that EI of the beam will be high in comparison to the column. So it will behave as a rigid frame. Okay, that basically as a shear frame. Okay, and we're going to see how much displacement is coming. For this case, our vertical displacement is coming and how much displacement we are getting in Abacus. So for all three cases, we are going to see. First case, for cantilever beam, how much displacement is coming as per theory, how much displacement is coming as per our Abacus modeling for cantilever beam, and for a frame where we are applying a lateral force. And next what we are going to do, we are going to model a rigid frame, and we are going to see how much displacement is coming as per theory and as per our calculation. Okay, so let us go to Abacus modeling. So here you just see what I did. Here you just see I make 4-5 model here, model 1, model 2, then I model mass spring systems, mass spring copy and point mass, like that. So here what you can do, you can, if you have one model and you need to change some parameter only, you can copy the model. If you have one model and if you want to change some parameter only, you are not interested for full modeling from the beginning to the end, you can do one thing, you can right click on the model and you can copy it. Okay, so like that, if you copy, you can create another copy of the whole model, and you can change some parameter and you can get some response. Okay, now see what I did. Initially I make a beam. Okay, so here I make the beam using your 3D wire element, 3D deformable and wire element. Okay, and next what we did, I provided property. The property here, you can see the property here is your 200 GPa and position ratio we have considered 0.3. Next we have assigned the section. The section here you can see profile section here. What I assume, I assume B is equal to 5 mm and depth also 5 mm. From the profile here you can see I consider B basically that width is your 5 mm and depth also 5 mm. Next what I did, I just assign it. I just assign this section and that material property. Here you can see section and the material property of the steel to this beam. Okay, and next to that what I did, I assign your orientation here. Okay, using these options we just assign the orientations. Next what I did, I just did the assembly, and next I do the meshing. The meshing, here you can see how many number of elements I have used. Here you can see how many number of elements I have used. Okay, so here you just see I have used 20 number of element. Okay, and next what I did here, you can see I assigned a static analysis. Okay, and then what I did, I applied a force. That force of that magnitude of the force is 1. Since I am doing static analysis, I assume this is the RAM type of loading in the direction of 1. Okay, and other end I just make it fixed. Okay, so now what I am going to do, I am going to run the job. Okay, and we are going to see how much displacement is coming as per our theoretical calculation, as per our numerical modeling. So here you can see we get our result. We get some result here from U1. Here you can see the displacement as per our final modeling is coming 3.192 times e to the power minus 2. Okay, so here you can see the Excel. I assign all the thing B, D, and then I calculated your second moment of inertia as B dq by 12, and E I assume 200 GPa. Okay, and length I have considered as a 1 meter, and here I applied 1 unit force. Okay, as per theoretical calculation, this is your PLQ by 3EI, that is coming 3.2, and as per Abacus modeling, that is your 1.398 e to the minus 2. Okay, so here you can see theoretical result and final model is very close. Okay, next what we are going to do, we are going to model it. We are going to model a frame. Next we are going to model a frame like this. Okay, and what we are going to do here, we are going to apply load at one end and we'll keep both ends are fixed. Okay, and if you run the job, okay, if you run the job, you can see how much displacement is coming. So here you can check what are the property are there. So here property 1 I assign for the beam, okay, that this beam, and property 2 I assign for the column part. Okay, so here you can see I have provided 200 GPa, okay, and so 200 GPa I can write 100 GPa and I can submit the job to. Okay, now we are going to see how much displacement is coming. So now job is completed. You can go to the result. So here you can see how much displacement is coming. U1. Here you can see displacement for the frame is coming 5.70 e to the power minus 3. That is our Abacus value. 5.0 e to the power minus 7. So here you can write 5.70 e to the power minus 3. Okay. 0.02 to the minus 7. Okay. Now as per theoretical calculation, this value is coming your 5.71 e to the power minus 3. Okay. Here you can see this value is very close. Okay. So we are using this formula. We are using this formula to calculate the lateral displacement occurring for a frame. Okay. So now what we did, we model a cantilever beam, and we also have modeled a frame, and we also observe how much displacement is coming. So here you can see we have calculated displacement is coming as per Abacus for cantilever beam 3.2, for the frame 5.70 to the power minus 3. Okay, now we are going to see how much displacement we can get if you have the rigid beam. Okay, if you have the rigid beam, that means we are considering this case. Okay, we are considering this case where your K equivalent is 24 by EI. Okay, so displacement, if your load is 1, okay, so you can calculate how much displacement is coming, and you can see how much displacement is coming as per Abacus calculations. So here what we are going to do, here in the property module, what we are going to do here, we are going to do the we are going to increase that stiffness. Here I am adding 1230 here, and I will give the run. Okay, so here you can see we have increased the stiffness by 1000 times. So we can see that the stiffness of the beam is high, so your rigidity EI term will be high in comparison to the columns. So you can assume that your rigid beam. So now you can see result is completed. Now here you can see how much displacement is coming. Displacement is coming as your 3.99 e to the power minus 3. Okay. So now here you can see as per theoretical value, that is coming your PL by 24 EI. Okay, and as per our Abacus model, okay, that is your 3.99 e to the power minus 3. Okay, so not like that you can calculate how much displacement is coming, and you also can calculate your equivalent stiffness. Okay, so here you can see for cantilever beam equivalent stiffness, that is coming 3.13 times 10, so 31.3. frame is 175, and here for rigid value, for rigid frame, that is your 250. Okay, now what we are going to do, we are going to model as a mass spring systems, and we are going to see if we provide this stiffness, we are getting this displacement or not. Okay, so for the frame also we are going to provide this stiffness, and we are going to see whether we are getting the displacement or not. Okay, so now what we are going to do, we will go to So what we're going to do, we're going to create a new model as model 4. Now here we're going to create the point. So here we'll use 3D deformable and point. Okay, and what we're going to do here, we're going to create that point. So here I'll give the coordinate as your 0, 0, that coordinate as 0 0.01 and 0. So here we have created the point. Next we are going to provide the property. Okay, so in the property module, what we are going to do, we are going to the special, and then here we are going to provide the inertia term here. Okay, so here we are going to provide as a point mass, and here we are going to select that point, and we are going to assign the mass. Here what we are going to do, here we are going to provide the mass as a 1 kg. Since we are performing static analysis, mass will not be factored here. Next, what we are going to do, we are going to define that in spring constant. We are going to define the spring constant. So here you can see it is saying that connect the point to the ground or connect 2 points. Since we have 1 point, what we are going to do, we are going to select connect the point to the ground options. Okay, so now we are going to select this point and we'll assign that the point is grounded, okay, or point is connected to the ground, and the spring constant, spring stiffness, here we are going to provide your 3.13 to the power 1, so 31.3. Spring constant we are going to provide is 31.3. okay, since this is your static analysis, there is no need to give the dashboard value, and now we can click OK. So here it is saying that choose the degree freedom. So here we are going to choose degree freedom as a 1. Okay, so this is your assign of your spring constant as well as your density or mass. Spring constant as well as your mass. Okay, since we are performing static analysis, your mass density or inertia term will not be a factor here. Next, what we are going to do here, we are going to define what type of analysis we want to perform. Here we want to perform static analysis. So we have selected that one, and loading here we have to define. Here what we are going to do, here before going to the defining loading, here we have to click on assembly, and here we have to click on dependent type instances, and we click OK. Next, what we are going to do, we are going to define the loading. So here we can apply as a concentrated force. We are selecting the point and we'll apply 1 unit of force and apple loading as a ramp. Okay, so now here you can see we have a mass spring systems. Though we are not able to see the spring here, we just assign that in that point there is a spring and there is a mass, and we are applying a unit force there. Okay. Next, what we are going to do, we are going to submit the job. So we are going to submit the job 4, and here we are submitting the job. So here you just see we assign spring stiffness, that is 31.3. So we should have a equivalent displacement. We should have equivalent displacement, that is 3.20 to the minus 2. Okay, so here result is completed. Now here we can see how much displacement is coming. So here you can see displacement is coming 3.195 to the minus 2. Okay, and as per our theory, it should be 3.2. So you can see that is your very close to our theoretical value. Okay, so here initially you just see what we did. Initially we model it as a normal beam, and we try to obtain how much displacement is coming. And since we know that force and displacement relationships, that is your displacement, that is your PLQ by 3I. Okay, so if you know how much displacement is there, you can calculate how much stiffness, how much equivalent stiffness the beam has. Okay, and same stiffness we can assign to the spring, and if you apply the same load, you should have a same type of displacement. So okay, same type of displacement. Okay, so here we are getting that if we model a cantilever beam as your equivalent mass spring system, then also we can get that same amount of displacement provided you calculate the stiffness, calculate the equivalent stiffness correctly. Okay, next what we're going to do, we're going to see how much equivalent stiffness is coming for the frame problem. So here for the frame problem, for the normal frame, we are having equivalent stiffness, that is your 1.5 to the power 2, that means 175. Okay, so what we are going to do, we are going to assign the stiffness. Okay, we are going to assign the stiffness. We are going to assign your equivalent stiffness. Okay, like this. So here we select 1 and here it should be 175. Okay. Now what we are going to do, we are going to submit the job and we are going to see whether our displacement is coming this much or not. 5.7 is, or it's 5.7, it's minus 3, this much amount displacement we are getting or not. Okay, so here you just see job is completed. Here you can see how much displacement is coming. Here you can see our displacement is coming 5.71 e to the minus 3, and as per our theoretical value is 5 to the minus 3. As per our frame problem, Abacus frame, it is 5.70. And if you consider a mass spring system, and if you provide equivalent stiffness, then also we are getting the same amount of displacement. Okay, so if you have any complex problem, if you have a very complex problem, in that case you can model it as a single degree freedom systems, and you can obtain your desired displacements or other quantity also. Okay, so next what we are going to do, next we are going to model it as equivalent mass spring systems, and we are going to see how much frequency is coming and how the damping is affecting our house. Okay, and next what we are going to do, we are going to model it. We are going to model a frame and we are going to perform model analysis of the frame. Okay. So here what we have learned, that we can model it, we can model a complex problem into a single degree freedom systems. Okay, and we can have sufficiently acceptable result. You can have acceptable result using your equivalent single degree freedom systems.